Okay. Um, Good evening, everyone. Am I audible? Please confirm. Okay.
Yes,
Okay. So, what happened? Yeah. So, hello and good evening, everyone. Welcome to this NPTEL live session on real-time digital signal processing offered by Professor Ratna Jain from IIT Bangalore. I am Shouharda Ghosh, first year PhD scholar in the electrical engineering discipline at IIT Gandhinagar. I have completed my dual degree from um, in electronics and electrical communication engineering at IIT Kharagpur with specialization in microelectronics and VLSI design. For everyone's convenience, I have also added my email ID, official email ID in this slide. So you may, in case if you are watching from YouTube later or in this live scene, so you can take these screenshot or copy it down. And these are PMRF sessions that will be taken every Monday from 8 to 10 p.m. So this is week 5 and we are currently in the second module of the course in which we are dealing with spectral analysis tools. So this week is a bit interesting because we'll be talking about DFT analysis and we'll pay a lot of focus on fast Fourier transform, a very popular, a very powerful tool for doing spectral analysis. So let's get started. Okay, so I have placed an agenda for today's session. So the topics that will be covered today are: first we'll do a brief review of the DFT, then we'll talk about twiddle factor, a part of DFT, and we'll see the properties of the twiddle factor, and then we'll study specialties like symmetry and periodicity, and then we'll talk about circular convolution. After seeing the importance of why circular convolution comes into picture, we'll look at the computational complexity of the discrete Fourier transform. And last but not least, we shall get into FFT. In the FFT or the fast Fourier transform, we shall be talking about radix to FFT, and we shall look into two versions, that is the DIT, decimation in time, and the DIF, decimation in frequency. We shall look at the derivation, how we shall go step by step into how DIT structures and DIF structures comes into picture, as well as their computational complexity. Then we shall end this session with a brief talk on finite word length effects in the FFT. Okay, so first let's get into the DFT review. So basically this is a course on DSP, which is digital signal processing, and whenever we talk about DSP, our signals are by nature discrete. They are digital, but I especially want to emphasize on the point that they are discrete. By discrete, it means that signals are defined only at integer samples 0, 1, 2, 3, and so on. This is obvious, but I'm just repeating over here for everyone's convenience. So these are defined in sequence. These are defined as sequences, so you can represent them in some kind of an array form: A, B, C, D, all that. We give an arrow over here to denote the 0th index, 0, 0, 0, depending on what you have actually. So since it is discrete, whenever we have a discrete time signal x of n, the corresponding spectral content or the frequency domain characterization is done by something called DTFT, or in other words, discrete time Fourier transform. So how do we define the discrete time Fourier transform? We all know x of omega is summation over all the indices from negative infinity to infinity, the signal x of n multiplied by the basis functions conjugate. Basis function is e to the power j omega n, so its conjugate e to the power minus j omega n. So what it says is that this signal x of n can be written as summations of various sinusoids, complex sinusoids of frequency, complex sinusoids of frequency omega. Now an interesting case over here is that unlike the continuous time signals where we can have an infinite spectrum from 0 to infinity hertz for our analog signals, however in the digital domain we are limited between 0 to 2 pi radian per second. And why is it so? It's because of something called sampling. So sampling, because we have a finite sampling rate, okay, fs. So what happens is that our analog frequencies map to digital frequencies in this way. Okay, so let's say analog, in analog we denote by this omega, and in digital or discrete time we denote it by this omega. So 0 maps to 0, 2 pi maps to fs, that is the full sample rate. So and sorry, is the opposite way around. fs maps to 2 pi. So any frequency f shall map to fs 2 pi upon fs times f. And as we very well know that our signal frequency should always lie between 0 to fs by 2, which in the digital sense would result in the omega lying between 0 to pi. So correspondingly, when we try to deal with signals in the digital domain, just like in the analog domain we deal in the S plane, the digital domain deals with something called the Z plane. So it's imaginary part of the Z, real part of Z, and the thing that is of interest to us is the unity circle, mod Z equal to 1. Now whenever we want on this Z, we write something as r e to the power j omega. So r being the radius of any, let's say any point Z, r this is the angle omega, this is the frequency. So it represents a kind of a complex sinusoid with an amplitude scaling factor of the r and the frequency component omega. Okay, so now when we talk about DTFT over here, DTFT means traversing around this entire unit circle. Okay, here this entire unit circle over here, you traverse around the entire unit circle. And when you traverse over the entire unit circle, what is the mapping that you perform? The mapping starts from f equal to 0, which corresponds to omega equal to 0. It comes over here, omega is pi by 2, which corresponds to a frequency of fs upon 4. This corresponds to omega equal to pi, f equal to fs upon 2. So this is the maximum frequency limit up to which our signal frequencies shall exist, and after that it is a complete repetition. Okay, so it's almost like a mirror image of the upper half of the z plane. It's a full repeat. But now you see x of omega lies between 0 to 2 pi, and for our convenience we shall evaluate it between 0 to pi, and then by virtue of conjugate symmetry, because let's say if we are analyzing real signals, then pi to 2 pi can be easily obtained by the mirror symmetry. Now the thing that is of concern to us is omega is continuous. Although our signal xn is discrete, omega is continuous. And imagine trying to evaluate x of omega at all omega. You can understand very well that this is really difficult. Okay, it's almost impossible. Why is it impossible? Omega is continuous, it's on the real line, and hence you have to calculate this all the points on the real line between 0 to 2 pi, and you can't do infinite computations. Our computer is a finite memory computer, and there is nothing called infinite memory in any computer. You may have terabytes, petabytes, yottabytes of memory, but then you have finite memory. So what do you do? For the sake of convenience, since we are dealing with a computer, we are working with digital real systems. The course name is real-time digital signal processing. We are dealing with machines which are real, so we need to be practical. So what is the practicality they do? We divide this entire omega into finite number of bins, okay, finite number of discrete points, and we evaluate x of omega at these finite points omega k, and these finite points are generally taken to be uniformly spaced. Okay, so in other words, what do we do whenever we have this z plane and you want to evaluate the DTFT? We don't evaluate it directly, we evaluate it at certain individual points over here, over here, over here. We evaluate at these points, okay, and then based on this we start our frequency domain analysis. So as you can see, let's suppose I take 8 points on the unit circle. So what are the points that we have actually? We started omega equal to 0, omega equal to pi by 4, omega equal to pi by 2, 3 pi by 4, pi, then this is 5 pi by 4, 3 pi by 2, then how much is this? 2 pi minus pi by 4, that's 7 pi by 4, and then back. You evaluate at these 8 points only, okay. So this is what? This is an n equal to 8 point DFT, discrete Fourier transform. You are discretizing the Fourier transform. So what you do, rather than evaluating x of omega, you evaluate x of omega k, and omega k is 2 pi k upon n, where k lies between 0 to n minus 1. So rather than x of omega k, for convenience we write it as x of k. And how do we calculate x of k? X of k is summation n equal to 0 to n minus 1, because what happened? Actually in this case we also assume our xn is finite length, 0, 1, 2, all the way till n minus 1, and in rest of the case the signal is absent, okay, at 0. So we do this x of n e to the power minus j omega k n. Now we know what omega k is, x of n e to the power minus j 2 pi k upon n into n. And in our previous sessions at the end of the class I had shown this notation. We have something, this is our DFT analysis equation. Why we call it analysis? Because we are finding the spectral components of the individual signal, okay, and we denote this e to the power minus j 2 pi n k n by w n k n, where w n is e to the power minus j 2 pi upon n, okay, and this is what we call the Tweedle factor, okay. This is an important term, this is a Tweedle factor, and this we will see very soon in our upcoming points, okay. This is a very convenient way, rather than always writing e to the exponential term always and always. You can just write wn and then continue with it, okay. So that's the Tweedle factor. So an important property to remember about this symmetry. What happens in symmetry? Omega n of k is equal to n minus k is minus omega n of k. Now let's see how is it true. So Wn of n minus k is how much? Wait, hold on for a second, let me check the property once. Sorry, yeah, it won't be this one, it is something else. So let's say this. So what? So here actually k lies between 0 to n by 2 minus 1. So what is happening over here? You have an entire sequence that lies between 0 to n minus 1, but then you divide it into halves. Here is n by 2 minus 1. So whatever you calculate over here, Wn by k, you don't need to calculate this over here. Okay, you can directly calculate the exponentials over here from whatever you have calculated in the left hand side. So let me show you how it's happening. Wn of k plus n upon 2 is how much? What is Wn? Wn is e to the power minus j 2 pi upon n. And now what we have in the exponent? K plus n upon 2. So now if you break it down, j 2 pi kn plus 2 pi n times n upon 2. Now if we evaluate it further, e to the power minus j 2 pi kn, and since this is a plus symbol over here, I separate the exponents, e to the power minus j, and then they cancel each other. And then they cancel each other, we get this e to the power minus j pi. Now this e to the power minus j pi is minus 1, and what is this? It was our very old Wn. See, the denominator over here is n, and here it is k. We ignore the 2 pi, Wn over k times minus 1, which is minus Wn k. Okay, so what am I trying to say? Let's look at this with n equal to 8. Okay, so n equal to 8 means in general k equal to 0, 1, 2, 3, 4, 5, 6, 7. Now do we need to really calculate this all of them? Let's see. Wn of 0 is fine. So we told you that it's up to n plus 2. Okay, so let's remember that n by 2 is 4. Wn of 1, let us calculate. It will be e to the minus j 2 pi n 0, e to the power 0 is 1, 8. So n minus j 2 pi by 8 into 1 minus j pi by 4. So how much is it? 1 by root 2 minus j by root 2. Wn of 2, e to the power minus j 2 pi by 8 times 2, e to the power minus j pi by 2. What is that? Minus j. Wn of 3, let's do this. 2 pi by 8 times 3, e to the minus j 3 pi by 4. So what happens over here? We are going down and down. So minus 1 upon root 2 minus j upon root 2. Okay, sine 3 pi by 4 minus sine 3 pi by 4, and cos of minus 3 pi by 4. Okay, so this is in the third quadrant, minus 3 pi by 4. Now let's look at Wn of 4. Wn of 4, or actually W8, n is actually 8, so I should have written here 8. W8 of 4 is how much? W8 of 0 plus 8 upon 2. Okay, and what did we see over here? We saw that Wn of k plus n Wn of k plus n by 2 is minus Wn of k. So what do we do? It's the minus W8 of 0. What do we get over here? Minus 1. See, we did not have to do any extra calculation. W8 of 5 is W8 of 1 plus 4. This is W8 of 1 plus 8 upon 2 minus W8 of 1. Negative of W8 of 1 is minus 1 upon root 2 plus j upon root 2. W8 of 6 is W8 of 2 plus 4 is W8 of 2 plus 8 upon 2 minus W8 of 2, and what is it's minus j, so its negative is j. W8 of 7 is W8 of 3 plus 4, W8 of 3 plus 8 upon 2 minus W8 of 3, and what is it? Minus minus, so all of them will be plus 1 upon root 2 plus j upon root 2. So you see, let's suppose you had some circuit to calculate these values. You have to calculate all the first 4, the rest 4 no need to calculate. Okay, and why am I talking about calculation? Because you see Wn of k, which is e to the power minus j 2 pi k upon n, what is it? Cos 2 pi k upon n minus j sin 2 pi k upon n. You have to calculate cosine, you also have to calculate sine, okay, both of them. So that's why I am talking about calculation. So in these cases over here, Wn of 4, Wn of 5, Wn of 6, Wn of 7, so in this case you don't have to calculate their corresponding cosine and sine. You can rely on the earlier calculations and then continue direct and then just do negative. Now how do I show them in a physical sense? I mean, how do I physically interpret them from our previously shown unit circle? Jagannath, if you have any doubt, please let me know. Okay.
Yes, sir.
Okay. The real part of z, we have the imaginary part of z. Sorry for this not so good unit circle is equal to 1. So when you are talking of n equal to 8, you take this is 0, so I should be like this. W8 of 0, where was this W8 of 0? It was at 1. Now we look at W8 of 1, it's 1 by root 2 minus j by root 2. So it's 1 by root 2 means the real part is positive, and minus j by root 2, which means this part is negative. So what is happening? Our next portion is actually located over here, W8 of 1, and then W8 of 2 is minus j, which is completely the imaginary part and in the negative direction. So this one is W8 of 2. So you can understand here what is going on. We are actually starting from here and moving in opposite clockwise direction, and we will be reaching here. Okay. So similarly, we can draw the other. Yeah.
Sir, I had a doubt.
Yeah.
Previously, you showed in different direction the arrow going for DFT.
When oh, uh, you're talking about this, right?
Yes, sir.
Okay. So here, what I'm showing over here is that here I'm showing that when I calculate DFT or DTFT, we move in this direction from low to high. Okay. But here, okay, when calculating DTFT, okay, now what I'm trying to show over here is that I'm not calculating DTFT here now. I'm simply talking about the twiddle factors. Okay, I'm just showing how. I'm not showing any movement or any calculation DTFT. DTFT is not being calculated over here. Okay, we are just showing here that where are the points located. Okay, where are the points corresponding to these um, twiddle factors located? What are the points where we are evaluating the DFT? Okay, so is that clear? I'm not
Okay.
evaluating this. Okay. Fine. So similarly, we go over here. It is W8 of, so hi Bella. So it's W8 of 3, and as I go further, hi, so it's W8 of 4. So so what happened here? W8 of 4. Now you see interesting thing, W8 of 4 is -1, and it is exactly opposite to W8 of 0. See, what did I prove over here? I did not know that there was some geometrical interpretation. I just directly showed you that Wn of k plus n by 2 is minus of Wk of k. Now you can see over here that both of them are oppositely directed vectors. Okay, W8 of 0 and W8 of 4, both of them are oppositely directed. So what can I write? This is minus W8 of 0. See, once I have calculated these first few vectors over here, I no more need to worry about the rest. Okay, the rest of them I can flip the vectors and they get the answer. Now what will happen over here? It's minus W8 of 0. Correspondingly, I flip this W8 of 1 around, I get W8 of 5, and that's minus W8 of 1. I flip this W8 of 2, I get W8 of 6, which is minus W8 of 2. I flip this W8 of 3 around, and I get W8 of 7, which is minus W8 of 3. So in that way, you calculate only n by 2 twiddle factors, and then you get the rest of the twiddle factors. In fact, this is actually one way in which we can reduce the complexity of the DFT, not by by almost 50%, but then the order remains the same. Okay, I'll tell you soon what I mean by that. So that's the symmetry property. Okay, and there's another property which is the periodicity. This is a bit simple, so much simpler than the symmetry thing. So what does it say? Wn of k plus n is how much? E to the power minus j 2 pi upon n, k plus n, e to the power minus j 2 pi n k times e to the power minus j 2 pi n upon n, and then this is e to the power minus j 2 pi, which is 1. This boils down to our old Wn of k. So what did we learn? Wn of k plus n upon 2 is minus Wn of k, and Wn of k plus n is minus is Wn of k. Okay, so these are two important facts about twiddle factor. Now what I had mentioned in my plan, so DFT review has been done. We have talked about twiddle factor and its properties. Now we shall talk about circular convolution. Okay, so now before circular convolution, why and how circular convolution? Okay, I will saying means how come it arises, not the exact. I won't be talking about the exact mathematics. So what happens is that whenever we convolve two sequences Xn and Sn, let's say this is an m point sequence. This is an m point sequence, this is an n point sequence. Both of them convolve to give yn, and let yn be an L point sequence. So can you tell me what is the value of L?
N plus 1. Forgot.
Okay. So actually it is m plus n minus 1. Okay. So you have an m plus n minus 1. Now what happens is that this convolution, let's say yn equals to summation xn. Okay, so how does the convolution look like? Convolution looks like something like x of k h of n minus k. K is sum from certain limit to certain limit, n1 to n2, let's say, depending on how the signals are placed. So you are doing these multiplication followed by add for all values of n, okay, and then you are doing lot of multiplications and then additions as well, and apart from that you are doing it for various values of n. Now one simpler method that you might think is that, why don't I, we know very well that convolution in time domain is equivalent to multiplication in the frequency domain, okay, but then we are not able to calculate x of omega and h of omega on computer directly. What we are able to do is x of k times h of k, okay. So actually what happens is that we take xn, we perform its so the thing over here is that x of k, if x of n is an m point sequence, then x of k will also be an m point sequence. When h of n is an n point sequence, h of k will also be an n point sequence. But then we want to find h of k times x of k. Oops, sorry for the symbol. H of k times h of x of k. But now see here, both the sequences have different number of elements, okay. This one is m points and this one is n points, so the multiplication won't take place at all. So what is the solution to this? We try to make x of n an L point sequence. What was L? L was the convolution, okay. L was the convolution sequence length. We make xn an L point sequence. How do we make that an L point sequence? Xn was already m point, so what do you do? Append L minus m zeros to xn. So in order to make things and what do you do with hn? Hn was an n point sequence. We also have to make it L point. So what we do over here? Append L minus n zeros to hn. So now what happens over here is that let me give an example. Xn is a 10 point sequence. It is convolved with hn, which is a 5 point sequence, okay. So what is your y of n? Y of n will be 10 plus 5 minus 1, which is 14 point sequence. So when you have xn, which is 10 points, from x of 0, x of 1 all the way till x of 9, what you do? You now add 4 more zeros to it. Okay, this is called appending zeros or zero pad. Similarly, what can you do with h of n? When you have h of n as a 5 point sequence, h of 0 all the way till h of 4, how many zeros do you append? Here I append 4 zeros, and here there are 5 because 10 plus 4 is 14. And here I have 5, and what do you add to get 14? 9. So you have 0 0. We again append, do a zero padding, okay. So this is what we do in order to ensure that our result is proper. So we take this xn, do some zero appending, hn, do some 0 appending, then we take its dft, we take this dft as well. Now we multiply the two dfts. What was the dft here? X of k, h of k, we get something that is y of k, and this y of k is actually the correct one because we appended the zeros getting the correct number of points, L point. So what I will do, I will take an idft over here and I will get y of n. Now actually if I do this, only then this yn is xn convolve with hn. Okay, now let's suppose for some reason xn and hn are of same length. Okay, let's suppose. So you might be thinking that okay, what's the need of appending zeros? Let's just directly apply, since they have xn as of same length, I'll directly do its endpoint dft, and I'll directly do this at the endpoint dft. And what do? I do, let's say I get something by multiplying them yk into xn. But then when you take its idft, you don't get yn back. What you get is something else, and the something else that you get is something called circular convolution. Okay, it's called circular convolution. And
Sir, can you repeat the difference? Like, how is it different?
see, x of n sequence is an endpoint. Okay, endpoint sequence. H is also an endpoint sequence. So what is y? How long is y supposed to be?
Uh,
-1, right?
m plus n minus.
Right,
Yes.
it's supposed to be m plus minus 1. But then what am I doing? I'm getting an endpoint sequence. So obviously there is some issue, some wrong issue going on, right? I'm supposed to get
Yes.
2n minus 1 point sequence, but because I've not done zero padding, I'm getting something else. So what I get is something called circular convolution. Now I'll show what happens actually as an example, and this will also help you in the assignments. Let's say xn is 1, 3, 5, 7, and yn is 1, 0, 0, minus 1. Okay, so now let's do the linear convolution by the normal method. So I write x of n terms over 1, 3, 5, 7, and I write here 1, 0, 0, minus 1. Do you know this technique?
Yes, sir.
Okay, good. 0, 0, minus 3.
Able to recollect.
Okay, no issues. So what I do over here, in the rows I list down all the elements 1, 3, 5, 7, xn, and hn I list down in the columns 1, 0, 0, minus 1. Now what I do multiplication. Okay, how do I multiply? Over here I multiply 1 and 1. Okay, over here I multiply 1 and 0. Okay, the row and the column I get the product. Here this row and this column I get the product. This row and this column I get the product. Okay, 7 into 1 is 0, 7 into 0 is 0, 7 into 0 is 0, 7 into minus 1 is minus 7. Now what do I do? Now
Addition.
no, now I draw boundaries. Okay, so it will be like triangular boundaries. First triangle will have only one element, one here. Second triangle will have these two over here, so I'll move like this. Then we will have another boundary like this, then move diagonally. Okay, it moved diagonally. Okay, move diagonally over here. We have moved diagonally. Now what do we need to do? Now we need to add we have separated them into these dotted regions. From each dotted region, add all the elements present. Like in this first dotted region, there is only 1 present, so I'll write here 1. Second dotted region, there is 3 and 0, so 3 plus 0 is 0. Sorry, 3 plus 0 is 3, I'll write 3. Then 5 and a 0 and a 0, so that's 5. Here 7 and a 0 and a 0 and a minus 1, that's 6. 0 and a 0 and a minus 3, 0 and a minus 5 and minus 7. Okay, so how much should be? 4 plus 4 minus 1 is a 9 point. Is it so? 1 2 3 4 5 6. Sorry, I'm doing silly mistakes over here again. It's a 7-point sequence, so it's a 1 2 3 4 5 6 7. So we have got a 7-point sequence. Now what happens actually when we try to do circular convolution? What actually happens when you do circular convolution? You are supposed to get getting 4 convolve with 4 multiplication. Xn and Hn is a 4 convolve with 4. So since you are multiplying xk into hk, the result will also be a 4-point sequence. So your y tilde of n will also be a 4-point sequence. So how do you calculate it? Let us copy this over here. If at any point of time you feel things are confusing, then please stop me. Okay, copy. Okay, so we had these things over here. Now what will we do in order to find the 4-point convolution? We break this block into groups of 4. Here is a group of 4, so we write here 1 3 5 6. But then now what happens? This remaining block, sorry, I missed a minus sign. This remaining block over here will overlap with this. So this was 0 position, this was 1 position, this was 2, and this was 3. So what happens is that this circular convolution, or the fact that you are not appending the zeros, is some similar to the aliasing in time domain. So because you have not given enough samples in time, these frequency domain contents are trying to overlap on each other. Minus 3, minus 5, minus 7. Understood what I have done over here? I have done 1 3 5 6. I have noted all of these first block elements first. Then the next block I am directly placing it down. So minus 3 will come on down on a 0. Minus, I am considering them again as a new sequence and placing them over the indices. 0 will have 3 minus 3, 1 will have minus 5, and 2 will have minus 7. Now I add them. Minus 3 and 1 is minus 2, 3 and minus 5 is minus 2, 5 and minus in minus 2, and 6. So see, if I had directly taken xn and hn and performed their DFT, I multiply them, then I perform their IDFT, then this y tilde n will give me this. And see the difference. Circular convolution will give us minus 2, minus 2, minus 2, 6. And what does linear convolution give us? 1 3 5 6, minus 3, minus 5, and minus 7. And hence you can understand the severe difficulty or the severe nuisance of not doing zero padding. Hence we must do zero padding before we do the DFT. Okay, so I hope this was clear. Any doubts in this? I hope there is no doubt in this. We shall now cover computational complexity of DFT. Computational complexity of DFT. Okay. So what we will do over here, is my voice audible, Jagannath? Here
Yes, sir. Yes, sir.
it's audible, na? Okay. So when we look into computational complexity of DFT, we'll again write the equation. It might look repetitive, but then as you repeat things, then it gets in your mind much deeper, and you get a better insight of things. Okay, because initially these equations look big, but later as you progress, you will get a good grasp of these things, and concepts will be much clearer. So if we look at uh, well, just a trivia before I talk about this computational complexity. You look at this DFT equation. What do we get in this DFT equation? X of k is summation over n equal to 0 to n minus 1 x of n e to the power minus j 2 pi upon n k n. And you, if you look at the IDFT equation, we have x of n is 1 upon n summation over k equal to 0 to n minus 1 x of k e to the power j 2 pi upon n k n. Okay, the look at both the equations over here. Look at both the equations over here. There's a summation, there's an exponential, and there's the original signal. Look at here as well. There's a summation, there's an exponential, and there's the signal, and a scaling factor. Scaling factor is not too much of a big deal, but you can see the great similarity in both the cases. Okay, so now let's suppose I have some ASIC chip where you given xn the n values, and you get x of k n values. Okay, you have n inputs and you get n outputs, and this actually calculates DFT. Okay, now first of all, can you use the same chip for IDFT? What do you feel?
Yes, sir.
Okay, so
Because it's similar. The formulas are similar, so I feel.
the answer is yes, and that's absolutely correct. So it's really good that actually we can use a single chip for both the purposes, because in communication systems we often have these FFT structures being utilized. So where at some point you have to do the DFT, and so automatically you have to do the IDFT or the IFFT at the other part as well. So uh, since they have the same structure, we can we don't need to develop a separate structure for this IDFT. We don't have to build a separate IDFT chip. We can use the same chip, multiple copies of that. Depending on where it's located, I will use that as either as DFT or as an IDFT. But then what modifications, but then my name, what modifications or inputs should be provided to the same ASIC chip for calculating the IDFT. You have this ASIC chip. Now this ASIC chip is something that you cannot open and tear and rearrange apart. It's something that's you have completely fabricated it from the foundry, and it's packaged in packaged, and all the pins are there, and you can use it anywhere. But then you can't, obviously you can't just tear it apart and rearrange stuff. It's not a discrete component circuit. It's an integrated circuit. So can you tell me what are, let's say I have the same chip again, what are the inputs that I should give over here to get Xn over here? Any ideas?
X of k.
Well, if you look what the chip does, the chip does something like this, something equal to summation over some index equal to 0 to n minus 1 times the output, let's say, times the input times w n something something. Okay, so if I put, let's say, whatever, based on whatever you have said, I put in x of k w n k n, and since k is a variable, k equal to 0 to n minus 1, so is this xn?
No, sir.
This is not xn. So what should we do actually? We need to look at this equation also. Copy. Okay, so now let us look at this equation carefully. We need e to the power j 2 pi kn, okay, and in the original thing we had summation x of n e to the power minus j 2 pi n upon kn. Okay, then let me tell you what to do over here. See over here, the first thing first, put the scaling factor inside. Once you put the scaling factor over here, you consider this itself as an input, a scaled input, e to the power j 2 pi n kn. Okay, now what I do a trick. The trick is very simple, it's nothing but change of variables. I define something like k prime equals to n minus k. Okay, what do I do? If k goes from 0 to n minus 1, k prime will go from 1 to n, and this, okay, let's write it first. K prime goes from 1 to n. So what is k? If k prime is n minus k, this implies k is n minus k prime. So k is n minus k prime upon n e to the power j 2 pi n. What is k? N minus k prime times n. And if we look at this, e to the power j 2 pi n n n, what's this? 1, right? So if I simplify this further, we get summation k prime from 1 sub n minus k prime upon n e to the power j minus j 2 pi n k prime upon n. So how will I give the inputs? Okay, so what happens at in k prime equal to n? K prime equal to n means x of n minus n, and that's x of 0. So let's say at that time I was giving it in the form x of that chip was receiving inputs. The order actually matters over here. That ASIC actually receives the inputs. X of 0 is the signal. Okay, so I should make curly brace cursive. X of 1, x of 2 till x of n minus 1, and it was multiplied by e to the power 0 0, e to the power j minus minus, all these things are there. Now what will happen if I put k prime equal to n? That means e to the power minus j 2 pi upon n times nn, and that is e to the power minus j pi, that is 1, that is again e to the power minus j 0. So that e to the power minus j 0 place will have an x of n, and what will e to the power minus j 1 have? You have to place k prime equal to 1. K prime equal to 1 meaning x of n minus 1. Okay, so this should not be x of n, this should be x of 0. X of 0, x of n minus 1, x of n minus 2, all the way till x of 1. Okay, so the ASIC will receive these as input. Okay, I forgot one thing, there should be a scaling factor also, so you can scale them beforehand. So the same chip which used to take x of 0, x of 1, all the way till x of n minus 1 as inputs, for DFT, for IDFT, what will it take? X of 0 upon n, x of n minus 1 upon n, x of n minus 2 upon n, all the way till x of 1 upon n. Okay, when you will be able to calculate the IDFT. Is this clear how all these tricks have been done?
Yes, so yes, it's clear.
Good. Okay, so this was actually, I got this question from Oppenheim's DSP book. Okay, yeah, so what were we supposed to do? We were supposed to see the computational complexity of the DFT. Now let's computational complexity of DFT. So what is this DFT doing? X of k summation over n equal to 0 to n minus 1, x of n e to the power minus j 2 pi upon n kn, and here k ranges from 0 to n minus 1. Now let me write this as wn of kn. Now if I expand this for a fixed k, see what is happening. X of 0 wn of zero into k plus x of 1 wn of 1 into k, x of 2 wn of 2 into k, all the way till x of n minus 1 wn of n minus 1 times k. Okay, so what is happening over here? Now I shall assume that xn is complex and x of k is also complex. Okay, so how many multiplications are there? We have n complex multiplications, and correspondingly we have n minus 1 complex additions. Now if you see a complex multiplication, it is equivalent to 4 so it is equivalent to 4 real multiplications. And okay, how 4? x1 j y1 times x2 plus j y2. So you simplify them, x1 x2 plus j x2 y1 plus j x1 y2 minus y1 y2. Let's group them into imaginary and real portions, plus j x1 y2 plus x2 y1. So there are 4 multiplications, you see 1 2 3 and 4, and there are 2 additions. Subtraction is also an addition, there is no difference. 4 real multiplications and 2 real addition. Similarly, a complex addition, obviously a1 plus jb1 plus a2 plus jb2, as simple as it can be, is a1 plus a2 plus j b1 plus b2. So there are 2 additions, you can see 2 real additions. So in calculating 1 x of k, we have 4 times n, 4n real multiplication plus, sorry, should not be a plus, and 2n plus 2n minus 1. This is coming from the complex multiplication, and this is coming from the complex addition. So how much is it? 4n minus 2 real addition. And how many x of k's do we have? We have n such x of k's. So what is our complexity? 4n square real multiplication and 4n square minus 2n real addition. What does it amount to? The computational complexity of DFT is of the order squared. So let's say when you are having n equal to 4, that time how many, and we should be more worried about the amount of multiplications, because multiplications, as I had told in the first lecture, are more hardware intensive and power consuming as compared to the adders. So when you have n equal to 4, so how many multiplication require? 4 square into 4, that's 64 multiplications. Now let's say you increased by 10 times, how many required? 4 times 40 square, there are 64,000 multiplication. Imagine the number of increase, and that's 100 times. Okay, so that's why, as you can see, this order of n square makes it really difficult to scale DFT to practical scenarios. Okay, because as I had mentioned over in our long back, when we are doing x of n convolve with n point, so depending on the total y n length that I am getting, I have to do 0 padding of x n hn. Now based on that, I may have some very small h of n, but then I may have to zeropad it to such an extent that the length gets in the order of 1000. We often have 1024 point sequences to deal with at every batch of time. Now when you try to do that, you can identify 1024 squared, that's almost 10 to the power 6, something like a million multiplications per sample. Okay, so that's really dangerous. So we have covered an important portion of our today's topic, that is computational complexity of DFT. And now in order to alleviate this, in order to get rid of this dangerous order of n square computational complexity, we will get into radix to FFT. We will see how it comes into picture. Okay, so far is it clear? Radix to FFT. And among radix to FFT, what is FFT? FFT is fast Fourier transform. But be careful, it's a misnomer. This is not a transform. It is not just like you might have heard of discrete time Fourier transform, continuous time Fourier transform, Laplace transform, Z transform, Z transform. You may have also heard of Hartley transform, Hadamard transform, Walsh transform, which are used in image processing. This is not a transform by itself. Okay, this is a fast algorithm to compute DFT. It is an algorithm that helps in calculating the discrete Fourier transform, and this algorithm can also be used in other similar kind of such algorithms like discrete cosine transform. So how does radix to FFT work? And radix to FFT also, these FFTs have two variants. One is the DIT, is called decimation in time, then DIF, decimation in frequency. So what happens due to in decimation in time? Well, before I talk about decimation in time and decimation in frequency, let me actually tell you what decimation is. Okay, so let's say you have a signal x of n. Okay, so you write it as x of 0, x of 1, x of 2, so on, so on, so on, infinite number of samples. Okay, now when we this block that you can see over here, this block that I have encircled over here, it is called a decimator block. And what does it do? Out of every sample, m samples, x of 0 to x of minus 1, okay, out of this entire set of m samples, it keeps one sample, the first one, and rejects the rest. Okay, it does not let the others count. Similarly, the next block contains x of m to x of 2m minus 1. It will only take x of m and reject the rest of them. So let me give you a simple example to make things clearer. Let's say I want to decimate by an order of 2. So how will it be? X of 0, x of 1, x of 2. Okay, now when I put x of n through a decimator, what will I get? I get the even samples only. I get this, I get this, I get this. I'll show what you will get. X of 0, x of 2, x of 4, x of 6, like this. Now let's say I shift x of n by 1 unit. What will I get? X of 1, this is the 0 point. Here this is the 0 point. X of 1, X of 2, X of 3, X of 4, X of 5. Okay. Now see the position: 0th position, 2th position, 4th position. What will I get now? X of 1, X of 3, X of 5, X of 7. Okay. I get even samples over here. I get odd samples over here. Okay. So let's suppose, is my voice audible now? Jagannath, Abhilasha. Hello. Hello. Am I audible? Hello. Hello. Jagannath, Abhilasha, anyone of you, can you please let me know in case my voice is audible or inaudible? Okay. I think they are not there. So let's say I have some sequence x of n and it's an endpoint sequence. For rest of the case, we'll assume n as even, and even more, it's some power of 2. So x of n is an endpoint sequence, x of 0, x of 1 till x of n minus 1. Now I want to calculate it DFT. So how do I write our very old formula? By now I think you have it's in your mind now. N will be 0 to n minus 1, x of n, wn, here also. Okay. Now what I do? I try to break this x of n into two parts. X of 2n, these are the even samples, decimated even samples, wn, k. Here the index changes from n to 2n, so here also it will change from n to 2n. Similarly over here, x of 2m plus 1, here also we will change from n to 2m plus 1. Okay. Now n equal to 0 to all the way till n minus 2. These are the even indices. Okay. Now when I go for n equal to 2m, what are the corresponding indices of m? M will be the half, 0, 1 all the way till n by 2 minus 1. So what does m range from? M ranges from n equal to 0 to n by 2 minus 1. Similarly here also m will range from 0 to n by 2 minus 1. Okay. Now see something. Wn of k2n, what can we write it? We can write this e to the power minus j 2 pi upon n k times 2n. Now I do some interesting trick. E to the power minus j 2 pi k m, this 2 over here I put it below n. Now you see the n over here was in the denominator. Now n by 2 is in the denominator. So how will it change? The previous factor can be written as w n upon 2 km. Okay. So how can I rewrite this? Summation n equal to 0 n by 2 minus 1 x of 2n w n upon 2 km. Similarly, here what can I write? N equal to 0 to n by 2 minus 1 x of 2m plus 1. Here I have a wn of k separated, w n by 2 km. Here because of this plus 1 I will take this out. Now this x of 2, what does it contain? Just simply x of 0, x of 2 till x of n minus 2. And how many points are present in it? It's an n by 2 point sequence. It's an n by 2 point sequence. I rename it as f of f1 of m. Similarly, what does x2m plus 1 contain? X of 1, x of 3, all the way till x of n minus 1. This is also an n by 2 point sequence. How can I write it? Let me write it as f2 of n. So what was our x of k? How can we rewrite this? We can rewrite this as x of k is summation over n equal to 0 n by 2 minus 1. I know it's lot of calculated stuff, but we will take this wn by 2 km plus, now I take that wn is outside, times summation n equal to 0 to n by 2 minus 1 f2 of m wn by 2 km. Now look at this very carefully. Look at this and look at this. f1 of n is an n by 2 point sequence. f2 of n also an n by 2 point sequence. Here this is n by 2, this is n by 2, and the indices also range up to n by 2. The indices also range from n by 2. So what do you see over here? I see. Okay, Jagannath, are you here? Abhilasha, are you here?
Yes, sir.
So, can you notice something interesting? We started with an endpoint FFT, and now what do we have here over here?
N by 2 point at DFT, sir. FFT.
DFT. You're correct. Okay, fine. So, we ignore the term, but then we call it an n by 2 point.
N by 2 point DFT. FFT.
N by 2 point. Let's name this as f1 of k. Okay. And this one is also n by 2 point DFT. f2 of k. So, what do we note over here? X of k is f1 of k plus wn of k f2 of k. So now what happens over here is that, oh sorry for this, I should have cleared this. X of k is f1 of k plus wn of k f2 of k. But there's a little confusion. Here k is ranging from 0 to n minus 1. Here k is ranging from n by 2 is 0 to n by 2 minus 1. Here k is ranging from 0 to n by 2, 0 to n, because we took it from our first definition. And here is ranging from, it will range from 0 to n by 2 minus 1. But then we are providing k as an input. What if k is greater than n plus 1? Okay. So what we do is that, let's replace k by k prime. 1 of k prime plus wn of k prime f2 of k prime. Now let us assume k prime is k plus n upon 2. Okay. So here k will lie between 0 to n upon n by 2 minus 1, and k prime is actually greater than or equal to n by 2. So for the indices of x which are greater than n by 2, what can I write? X of k plus n by 2 f1 of k plus n by 2 plus wn of k plus n by 2 f2 of k plus n by 2. Now we shall use the old properties which we had learned just an hour back. Where did we learn it? Yeah, we learned this symmetry property. Look at this, wn of k plus n by 2 is minus wn of k. And then we also learned this periodicity, wn of k plus n is wn of k. f1k and f2k are periodic over n upon 2, because we have seen that earlier. So f1 of k plus n upon 2 will be f1 of k, and f2 of k plus n upon 2 will be f2 of k. Okay, and wn of k plus n upon 2 will be minus wn of k. So what will happen to x of k plus n of 2? It will be the same, f1 of k minus wn of k f2 of k. Okay, so now what do we have? The entire equation x of k is f1 of k plus wn of k f2 of k. So k plus n by 2 is f1 of k minus wn of k f2 of k. Okay, so now we see what happened. We are breaking one n point DFT into two n by 2 point DFTs. Okay, similarly, if I want, I can do the same with f1 of k. f1 of k, I can break it into two parts, v11 of k and v12 of k. This is an n by 2 point DFT and these will be n by 4 point DFT. So what will I be able to write? f1 of k will be, just look at this previous one, x, sorry, s, this is n, all of these are n by 2, this is n over here, v11 of k plus w, here is an n by 2 point sequence, so n by 2 over k, and v12 of k, f1 of k plus, here it was n by 2, here it will be n by 4, v11 of k plus w, okay, here it will be minus by 2 k v12 of k. Similarly, we can write f2 of k is v21 of k plus wn by 2 of k, v22 of k, f2 of k plus n upon 4 is v21 of k minus wn upon 2 of k, v22 of k. Okay, now let's try to first draw this. So let's suppose, what was the f1 of 0? No, sorry, not f1 of 0. Let's suppose we want to do for n equal to 8, or f1 of n was actually the even samples. What will be the even samples? X of 0, x of 2, x of 4, x of 6. And when I further divide this, what will happen? These will go to v11 of n, x of 0 and x of 2, x of 4, sorry, and these will go to v12 of n, will be x of 2 and x of 6. Similarly, f2n, we shall have x1, x3, x5 and x7. If I am going little bit fast, please let me know, I can slow down. v21 of n will have x1, x7. Okay, so I hope that speed is fine. x1 and x5, and I take the alternate samples, v22 of n as x2 and x7. Okay, so first let's deal with f1 and f2. How will I deal with it? I put them in some order, x of 0, x of 4, x of 2, x of 6. This was our v11, this was v1 2, I write them as f1. I put them into a 4 point DFT block. This will require some more space. Here I have another 4 point DFT block, and what are the inputs to this? What is the main percentage actually? I think fast x of 1, x of 5, x of 3 and x of 7. This one was So what will I get over here? F1 of 0, F1 of 1, F1 of 2 and F1 of 3. Here what do you get? F2 of 0, F2 of 1, F2 of 2 and F2 of 3. Okay. Now we want what? We want this x of k. Okay. Now look over here. Am I audible now? Am I audible now, Jagannath? Hello.
Audible, sir. Audible, sir.
Okay. So did you hear? Did you see this part? F0, F1, F1, F0, all this.
N by 4 point F50.
Huh. No, these are n by 2 points. Okay. For now, these we are
Yes.
dealing with the n by 2 point FFT. So what we'll do now? We'll try to combine them. And how do we combine
Okay.
them? Let us now look. So here, Abhilasha, can you mute yourself once if you are not saying anything?
Sir?
Can you mute yourself if you are not saying anything?
Okay, sir.
Okay. So you see over here, F1 is as it is. F2 of k in both cases are multiplied. F1 is as it is in both the equations. F2 is pre-multiplied by Wn of k in both the cases. Fk, k, it's multiplied. Okay. Then the separate thing is that for x of k it's a plus and x of k plus n by 2 is a minus. So let's see what we actually do over here. Here k is 0, so it will be W8 of 0. Here k is 1, here k is 1, so W8 of 1. Here k is 2, so W8 of 2. Here k is 3, so W8 of 3. Okay. So now we have all these addition terms. Now what we will do? We will now try to add them. I would rather place them over here. All of them are 1. F of 0 goes over here, 1 goes over here, this goes over here, and this one goes over here. Similarly, this one goes over here, one goes over here, one goes over here, and this one goes over here. What do we get over here? X of 0, x of 1, x of 2, x of 3. And for x of 4 to x of all of them were plus. Okay, whenever I am showing, whenever two nodes, two branches meet at a point, that's a summing node. You have a signal x and you have a signal y. The output over here will be x plus y if there is no negative sign given at any of the edges. Now we saw in x of k that there is a positive sign, so you won't add anything. Okay? Positive sign over here, but here for k plus n by 2 there is a negative sign, so we have to add this negative sign over here. Negative, 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 and negative. So what do we get? X of 4, x of 5, x of 6, x of 7. Okay? So here you can see what we have done. We have 4 complex multiplications and then we simply do addition. I have broken this 8 point DFT into 2 4 point DFT. Now I can also break this 4-point DFT into 2-point DFT. How? Let me show you. X of 0, X of 4, X of 2, X of 6. So V11 and V12. What will I do? I'll break this into, put it in a 2-point DFT block. 2-point DFT block. And what I get? V110, V111, V120, V121. Okay. Now what I do over here? Here n is 4 over here. Okay. Here n was 8. Here we are dealing with n equal to 4. So what are the terms that we should multiply with? Here W4 of 0 and W4 of 1. Now we shall try to add them. Okay, so see what will happen here? Minus, and this was V11. So actually this was our F1. So F1 of 0, F1 of 1, F1 of 2, F1 of 3. So now a 4-point DFT you can see has 2 complex multiplications and 2 points. And now what is a 2-point DFT? 2-point DFT is a very easy structure, easy and simple. It's something like x1, y1, x2, y2. x2 is x1 plus y1, y2 is x2 plus y2. This is our 2-point DFT structure, and this is called a butterfly. This is called a butterfly. So an FFT, as you can see, these are elongated. Can you see over here? These are also butterflies over here. This
Yes, sir.
this is a butterfly. This is a butterfly. Here also in the 8 point, this is a butterfly. This is also a butterfly. This is also a butterfly. This is also a butterfly. Okay. So this FFT structure is full of butterflies as well as twiddle factor. These are twiddle factors. These are also twiddle factors. Even in this case, there in a since it's a 2-point DFT, there will also be a twiddle factor. Here it's n equal to 2. So we'll have twiddle factors W2 of 0 and W2 of 1. But then W2 of 0 is actually 1, this is minus 1, so we don't show them. So actually FFT is full of butterflies and FFT and this and you can see over here what has happened. We have actually broken down our system into 3 stages. This is our stage C, our stage 2, and this 2 point, this is our stage 1. Okay, so how many stages are there? There was n equal to 8 and then 3 stages. So if you look at the entire picture, what will happen? We will have 4 2-point DFTs, and these 2-point DFTs will have their own we will have the butterflies over here. oh sorry. So these 2-point DFTs actually go and combine together, and plus a 4-point DFT block, 4-point DFT block is also go in the combine. I won't say this is a 4-point DFT anymore, this is a combined block, and then all these 8 go together in a combined block. Okay, so this 2-point is also known as DFT, it can call it as a combined block. So there are first stage, second stage, third stage. So log 2 base 8, that's 3 stage. So the number of stages are log 2 base n, and each stage has some of the order of n multiplications. Hence the computational complexity of radix to FFT is order n log 2 base n. It actually contains n by 2 log 2 base n complex multiplications. Okay, so now see, DFT was n square, radix to FFT is n by 2 log 2 base n. Okay, so have you seen this reduction in the complexity? This results in decrease in the hardware count. Okay, and actually it's n by 2 log 2 base n, but if you see further, we have actually exploited the symmetry properties of these twiddle factors. Okay, so because of twiddle factors, and then over here we have removed twiddle factors since they are just 1 and minus 1, so the actual number of multiplications are even lower than that. Okay, so this is the decimation in time. Okay, so why was it called decimation in time? Because we were breaking the sequences in time domain. Okay, and you see the order x of 0 in bit system, 3 bits. How do you write 0? 0 0 0. How do you write 4? 1 0 0. How do you write 2? 0 1 0. How do you write 6? 1 1 0. How do you write 1? 0 0 1. 5 1 0 1. 3 0 1 1. 7 1 1 1. How do you obtain this? How can you obtain this? This is actually called the bit reversal. Okay, the bit reversal addressing. Okay, I had mentioned this very well in the first lecture as well, that how you obtain them. You have 0 1 2 3 here, so if I look at them and normally write there 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now if you try to reverse the bits, that is from here to here, 0 0 0, what is that? It remains 0. Here what will happen? 1 0 0, it becomes 4. 0 1 0, this becomes 2. 1 1 0, this becomes 6. 0 0 1, that's 1. 1 0 1, that's still 5. 0 0 1, that's 3, and 1 1 1, that's 7. So in the normal order, when you do bit reversal, this is the way in which you access your elements, these signals, and we have decimated the signal in time domain. Okay, we have taken the signal x of 0 and taken even samples, then further taken their multiples of 4 and then shifted by 2 4. Okay, that's why it's called decimation in time. Now what we can do, and one important thing, the unit structure for a radix to dit is actually this wn k this is the unit structure of a reduced to dit, which consists of the twiddle factor and the butterfly. Okay, so you get a and b, and you get a plus b w n k and a minus b w n k. Okay, now we have something called DIF, decimation in frequency. Okay, so how do I do this? Here I play a different trick. X of k is summation over n equal to 0 to n minus 1 x of n wn of k. I let it remain as it is. Now we know that k ranges from 0 to n minus 1. K can be even and k can be odd. Now what I do, rather than choosing the time instance x of n from even and odd, I choose the frequency domain samples x of 0, x of 2, all the way till x of n minus 2. I calculate them separately. How? X of 2l. Let me see how does it work. X of n wn 2l n. Okay, now what would I like to do? I want to put these two down. wn 2l of n, you can write here wn by 2 l of n. I hope you know how. That's because we did it somewhere previously. Where did we do it? Yeah, over here. Yeah, wn of k 2m, here it goes down. Similar way we do it over here. Okay, but then n is actually ranging from 0 to n minus 1. So what we can do is that we can break this into two parts, because wn by its repetitive bit n by 2. Okay, x of n wn by 2 ln plus, again we write this as n by 2 minus 1, but this time we have the values after n by 2 minus 1. Here this will also be the same. Did you understand how did I write this step? N by 2 minus 1 minus n equal to, okay, x of n plus x of n plus n upon 2 wn upon 2 ln. So you see what happened. Now this is again a n by 2 point DSP. This is the x of 2l. And then how do I calculate x of 2l plus 1? This will be calculated as n equal to 0, l minus 1 plus n wn n 2l plus 1. Go for the break it up, plus n wn upon 2 l upon l into n. Okay, so what we do, hold on a second. So we actually once again break it up. 2n by 2 minus 1 x of n W n of n W n by 2 ln, and let's suppose for another one n prime equal to 0 to n upon 2 minus 1 x of n prime plus n upon 2. So these are the ones after n plus 2, and then W n is n prime plus n upon 2 W n upon 2 ln, and we again I am repeating, this is the symmetry property, is W n prime. So now I combine all of them and I will be able to write n by 2 minus 1 x of n minus x of n plus n by 2 W n times W n by 2 ln. Again this is a n by 2 point DFT. I have no more drawing the structure. I can show it in the screen. I will show you in the screen now how it looks like. But then here are the radix 2 DIF structures, important unities. Of n plus n upon 2. Okay. You see this structure over here and this structure over here. Then what happens is that this structure is something called the transpose of DIT. I hope you know what transpose is. I had taught this in the third lecture, I guess. So DIT and DIF are transpose of each other. And an important point to know over here is that radix 2 DFT consists of this single complex multiplication, which amounts to 4 real multiplication and 2 real addition, and we have 1 2 we have 2 complex addition, which means we have 4 real addition. Now if we add them, we have a single butterfly consumes 4 multiplication units and 6 addition units in one butterfly. Okay, and last few minutes, I know it's almost night, so let me leave very early. Yeah, so these were the slides. So these are the things that I had been showing you for a long time. So this is the DFT versus FFT efficiency. You can see that as your n increases, the number of multiplications ratio becomes higher and higher. The FFT becomes more efficient with higher values of n. This was the bit reversal that I was talking about, that how you do the bit shifting and get the equivalent number. These will discrete in decimation in time frequency, where you have the 2-point DFTs over here, and then they're combined, and then they've combined the 4-point DFTs and so on. Okay, I hope these slides are available in the course website. Same for the decimation in frequency, and as I told earlier, that decimation in time and decimation in frequency are transpose of each other. So here you can see there are 4 2-point blocks in the beginning and 1 combination block in the end. Here is the other way around. Rather than combine, it's a reduce to 4-point DFTs and reduce to 2-point DFTs in 4 points of the end. And then let me tell you briefly, there is certain finite word length effect in the FFT. And why does this happen? There are 3 cases. One is there are the multipliers over here. So because when you multiply 2 k-bit numbers, you get a 2 k-bit number output. But then because of saving the hardware, you don't keep that 2 k bits, you keep the KMSB bits. So when you truncate the other KLSBs, then there is some error introduced which we call the round off error. And then there are overflow errors which happens in case the multiplication product does not fit into the word length of your filter of the output register. We should always avoid this at all costs. And then there are coefficient quantization errors which happens because the twiddle factors, the cosine and sine, you do not express them as finite number of bits. Okay, so that's shown over here, that round off noise, as I told you, there are 4 real multiplications, and multiplications are having this approximation. So the noise, since let's suppose that the output is b bits, so the variance due to b bits is given by q square upon 12, and q is 2 to the power minus b minus 1, assuming it's uniformly distributed noise. So it's q square by 12 is the variance for a single multiplier, and there are 4 multipliers, so 4 times q square by 12. And then what happens is that this propagates to n stage. There are n such stages, so sigma naught square is n times the each multiplier, each butterfly noise, and each butterfly is contributed by 4 multipliers. So that's n by 3 to the power minus 2b minus 1. Any confusion in this, how this noise is coming? Jagannath, Abhilasha? Any idea, everything clear how this noise is coming? Okay, you want to know how this noise is coming? Good, I'm glad that you asked it. So what happens is that whenever you have some large k-bit number and you truncate that to b bit, okay, and the assumption is that the signal lies between -1 and +1. Okay, so what happens is that the finite steps, okay, the finite steps delta is the full scale range divided by the total number of steps. There are b bits, so b bits means 2 to the power b levels. I'm not if you have looked at the first lecture, then these things were first or second lectures, then these things were covered. So it is 2 by 2 to the power b, so this delta is 2 to the power minus of b minus 1, and we are assuming that this delta, that this quantization noise is uniformly distributed between minus delta by 12 to plus delta by 12 with a probability density function 1 upon delta. Is this clear? Uniform density, we are dividing the range between 1 to -1 by b bits, that's 2 to the power b levels, and then its uniform distribution, so minus del by 2 to del by 2. So variance of this x is actually del square by 12. I'm not doing the derivation, it's very simple, you can do it on your own. Minus del by 2 to del by 2 1 by del x square dx, that's it. The variance will come out to be del square by 12. So 1 multiplied contributes, this is del 2 to the power minus b minus 1 whole square by 12. So that's 2 to the power minus 2 b minus 1 by 12, and 1 butterfly has 4 multipliers, so 4 times 2 to the power minus 2 b minus 1 upon 12, that's 2 to the power minus 2 b minus 1 upon 3, and there are n stages, so for n of them, n by 3 times 2 to the power minus 2 times b minus 1, and then the signal power is okay, so they will be given only the noise power. So I hope this is clear. So here what they have assumed is that the signal is also distributed uniformly between -1 to 1, and hence the corresponding power is 1 upon 3. So the signal to noise ratio is noise due to signal and noise due to the multiplier, sorry, power of signal by power of noise, 1 upon 3 by n upon 3 to the power minus 2b minus 1, that it will go 2b minus 1 upon n. So for every stage of if you increase every the number of stages, they need to increase the number of bits also to maintain the same SNR. Okay. Oh. So there are I think you should note these slides as well. There are a lot of okay, it's clear. So I'm not explaining the other slides further because they are based on the same concept. Now I hope you can easily follow whatever is written over here. The main thing was how you derive the original signal to noise ratio, and then based on different conditions, the scaling and all, they will perform differently. These slides are available in the course web page at Swayam, so you can refer to them as well. There's nothing much extra to do. It's all this, and you can look at this practice problem as well. Okay. So it's 9:57 already. So I hope you had you understood the FFT concepts as well. FFT, DFT, we had covered a great number of detail today. Okay. So I think, yeah, we have covered almost everything in our plan. So we can stop for today. Okay then, good night.